Hi, this is Peter with CalcBook, and today we're going to be looking at a double angle in compression. So we're going to be taking a look at the AISC Spec Chapter E for compression, and within that we're going to be using E6 for a built-up member, and we'll talk about that in a second. And then that will refer us back to E3 or E4 for buckling capacity, so flexural, torsional, or flexural torsional buckling. And then we'll look at E7 if we need to for slender elements if that applies. And just as a quick refresher, right, a built-up member is basically two individual components or two elements that are bolted or welded together along the length of those members, which creates that built-up shape. And the most common, or one of the most common types of built-up members is a double angle, right? So you can see you basically have two individual angles that are bolted together or welded together along the length of that member. So let's take a look at our problem statement. We are going to assume that we have a 2L 4 by 3.5 by 3/8, and that's going to be long leg back to back, right? So that's going to be these long legs are back to back or vertical. We have a 3/4 inch separation. It's going to be an 8-foot long member with pinned ends. Our dead load applied is 20 kips, and our live load applied is 60 kips. And we are going to assume a spacing between connectors of 32 inches, and those connectors are going to be pre-tensioned bolts. And we'll talk about what that means when we get into the calculation. So let's go and open up CalcBook, and we'll get started on the design. All right, we've got CalcBook open now, so we can go ahead and click into our AISC 16th edition. We're going to be looking at a member design, a steel member, and then we're just going to be looking at the axial design calculation. So we can start to enter in some information here on the left side. You'll notice that we've updated a little bit of the user interface here. Just put the loading up top and then the defined shape below, and then made the drop-down selection a little more consistent. So for our load source, right, it doesn't matter, beam analysis or user entered, because for axial design, we will just be entering those loads in manually. We are going to be using our AISC 716 load combinations, and then a standard shape, and then we're going to select our 2L. And then we're going to scroll down until we get to our 2L 4 by 3.5 by 3/8. And then we have a 3/4 spacing there with our long leg back to back. So that is the member we want here. So 2L 4 by 3.5 by 3/8 by 3/4 gap, long leg back to back. Okay, and then we can go ahead and jump into our axial design. So we are going to do a compression design. That's what we have selected, so we'll keep that there. So torsional and flexural torsional buckling. We are going to be checking this, right? So if you open up this tooltip, this does apply to us because we are a singly symmetric member. So we will go ahead and enable checking for torsional and flexural torsional buckling. Our unbraced length is going to be 8 feet. And we said we had pinned connections, so we're going to leave our effective length factor at 1. And then our distance between connectors is 32 inches. And then our connection type is going to be a pre-tensioned bolt, right? So we're going to click on the second option here. All right, and then we've got all of our capacity inputs entered. So we want to go over to our demand. We have a dead load of 20 kips and a live load of 60 kips. Perfect. All right, we can jump into the design now. So we can go take a look at our demand, right? So we're going to be load combination 2, right? So 1.2 dead plus 1.6 live. And then the first thing we want to do is check for our slender elements to see if we have to use section E7, right? So we check for the flange, right, or one leg of the angle, and it is non-slender. And then we check the web or the other leg of the angle, and it is also non-slender. So we don't need to use E7 for this calculation. We're just going to be using chapters E3, E4, and E6 from the AISC spec. So the first thing we want to do is calculate our slenderness ratio, right? And this is where it's a little bit different for a built-up shape, right? We check it normally about the x-axis, just our KL over R value. But then for the other direction, right, we have to include or account for the spacing of our connecting plates, right, our connecting bolts. So we calculate a modified slenderness ratio, which is this A over Ri, so the spacing over the radius of gyration for one of the angles. And then we use that to calculate the modified slenderness ratio of the member, of that built-up member. Right, so that's going to be sort of the individual or the total section, KL over R about the y-axis, and then we add in this term for accounting for the spacing of the plates. And that gets us a modified slenderness ratio of 61.01. And then from there, right, we can go into our buckling calculations. So first we check E3, flexural elastic buckling stress, and we're going to take the maximum of our modified slenderness ratio, which is 61, and our slenderness ratio about the x-axis, which is 76. So our x-axis still controls, which is what we want, right? We have control over the spacing of the plates, so we've spaced the plates close enough that the x-axis controls. And then that gives us a buckling stress of 48.5 KSI. But then we also need to calculate our torsional and flexural torsional buckling stress. So we calculate first about the x-axis, right, which gives us 48.5, and then about the y-axis, which gives us 76.9, and then about the z-axis, which is this equation 4-7, and that gets us 101.6 KSI. And then from there, we can also calculate the torsional buckling stress, which gets us 60.37 KSI. From there, we figure out what the controlling buckling stress is, right? So between the flexural and the torsional, and that is going to be limited by our flexural buckling stress of 48.5 KSI. From there, we run through the rest of our E3 calculations to figure out our buckling stress of 26.4 KSI, and then finally our design compressive strength, right, just the Fn times Ag, which gets us a total compressive strength of 127.3 kips. And our demand for this was 120 kips, and so our demand to capacity ratio is 0.94, which means we are okay. So that is a built-up member in compression, or a double angle in compression using CalcBook. We hope you guys enjoyed this video. If you would like a 25% discount on your first month subscription of CalcBook, you can use the discount code YTCB2024, and you can use that during checkout. I hope you enjoyed the video, and we'll see you next time.